Okay, I'm making the guess that the intent was for this problem to be solved using partial fraction decomposition instead of any other techniques, especially based on this hint right here. So here's the original function for which we want to find the antiderivative. And here is the partial fraction decomposition, which we're going to talk about on the next board. And here's another way to write it. In other words, we can put each term of the numerator over this denominator. And that's going to enable us to find the antiderivative of each fraction or each term. And this is the antiderivative right here, which was found by kind of putting indefinite interval signs in front of each of these fractions and using the proper technique. Okay, and notice that all of these, the first four graphs have this, or functions have the same graph. This green graph is the derivative of big F, which should give us little f. And they are indeed identical. So the question is, how do you get from here to here? If we go to board 2, these factors in the denominator are irreducible quadratics. That is, if you set them equal to 0, there's no real numbers that satisfy that equation. Or you could say the discriminant is less than 0. So that means that the partial fraction decomposition will look like ax plus b over this irreducible quadratic plus cx plus d over this irreducible quadratic. And to find the values for a, b, c, and d, we're going to use a technique called equating coefficients. So if we multiply both sides of this equation by the least common denominator of all the denominators, which would be x squared plus 1 times x squared plus 25. On the left, we'll just get that numerator. And on the right, the x squared plus 1s will cancel out, and we'll get ax plus b times x squared plus 25, and plus cx plus d times the quantity x squared plus 1. Now, if we remove the parentheses by using FOIL to multiply these two binomials together, we get something like this, plus something like this, and here's where equate coefficients comes into play. So the coefficient of the x cubed term you can think of as a plus c, the quantity times x cubed, but there is no x cubed term over here. So that means that a plus b must equal, a plus c must equal 0. And likewise, the coefficient of the x squared terms is b plus d, that has to equal 17. The coefficient of x is 25a plus c, but the coefficient of x is negative 48. So similarly, 25b plus d has to equal the constant term, because there's the constant 25b plus d. So there's a system of 4 equations, 4 unknowns. It's pretty easy to solve them because this pair doesn't have a b or a d in it. If you subtract the second equation from the first one, you get a is negative 2, which means c has to be 2. And likewise, b equals 7, d equals 10. So there is the partial fraction decomposition. And as we showed on the first board, you can break that apart into 4 fractions. You'll be using u substitution on this one to get minus the natural log of x squared plus 1. This is inverse tangent. I didn't put the dx's in here, obviously. And this one's a little bit trickier, but in the end, you get 2 times the inverse tangent of x over 5. I'll let you worry about that one. There you go. Hope that helped. If you have any questions, post a comment.